screencast is about statistical significance. In this, we'll cover the meaning of statistical significance, p-values, confidence intervals, and error bars. So I want to start out with what statistical significance means. First of all, it's different from meaningfulness. It's not significance in terms of having a meaning, being important or meaningful. It's significance purely in terms of mathematics. The formal definition is statistical significance is the likelihood that a relationship between two or more variables is caused by something other than random chance. So this is an acknowledgement of the fact that our world is uncertain, coincidences are fairly common. Many times things happen by random chance. And unless we have statistical significance, some researchers will assume that any relationship between two variables is due to chance alone. So statistical significance is a way of quantifying the probability or likelihood that a relationship is meaningful as opposed to just a result of the randomness and uncertainty of the world. But again, this is mathematical significance. It's not actual significance. So one way that we use to look at how likely it is that a relationship between two variables is due to chance alone. If it's not due to chance alone, it's statistically significant. So a way that we determine if the relationship between two variables is likely statistically significant or not due to chance alone is a concept called p-values. And so a p-value is a percentage that this is due to chance alone, or a percentage of the probability or the likelihood that the result you have is due to chance alone. Kind of the standard that that is conventionally agreed upon is a p-value of 0.05 is statistically significant. And what that p-value of 0.05 is saying is that there is a 5% chance that your results are due to chance alone. Because there's only a 5% chance that your results are due to random chance alone, there's a 95% chance that your results are due to something other than chance. Another way to think about p-values is, let's just say there was a fictional politician in our world somewhere, perhaps in Washington, D.C., who was really in support of denying rights to people who are gender nonconforming or transgender to use bathrooms, to use public bathrooms. And let's just say that a group of people, noting that we are, many of us are being denied access to public bathrooms where we generally pee, we've decided to pee on that the only option left to us is to pee on the lawn of this certain fictional politician. And convention has established that in order for this politician to be able to walk to work, there needs to be at least 5% of his yard needs to be grass. Once 95% of his yard is covered in pee, it becomes impossible to walk to work. So there's a picture, this line here, the second bar is a picture, the second bar from the top is a picture of a p-value of 0.05. So this green here represents the grass, or the idea that the results we have are due to chance alone. However, so we see here that there's a 5% probability that the composition of this individual's yard is due to chance alone, which means there's a 95% chance or probability that the amount of pee in this individual's yard is due to something other than random chance. So, I mean, there could be random reasons in the world that occasionally there might be pee in a person's yard. Someone's child is walking to school and has an urgent bathroom situation. My dog comes by and pees on your yard. So it is possible that someone could have some amount of pee in their yard and have it be due to chance alone. But the p-value tells you what the probability of that is. So here we have a p-value of 0.01. And because p-values, they're percentages expressed as decimals, so we move this decimal point over 2, and we see that this is a 1% chance that the yard, in other words, the yard is 1% grass and 99% pee, which means our fictional politician can't get to work, and that there's only a 1% probability that the amount of pee in the yard is due to chance alone. There's a 99% probability that the amount of pee in the yard is due to this fictional politician's policy decisions, limiting access to public bathrooms, resulting in the fact that we now need to pee in his yard. This p-value here, 0.06, that means there's a 6% chance that the result we have is due to chance alone, and a 94% chance, or probability, that it's due to something other than random chance. However, with 6% grass in the yard, our fictional politician friend can still walk to his office and enact some dangerous, harmful legislation. So this is not an acceptable p-value. So this lets us know that there's a likelihood that what we're seeing is just due to chance alone. Likewise, this is a p-value of 0.5, which, when we move the decimal place over 2, translates to a 50% chance that the pee in the yard is due to chance alone. So that is a more disgusting way of thinking about p-values and statistical significance. Always ask yourself, how much pee in your yard do you need before you believe that the pee in your yard is due to something more than random chance? One thing I want to highlight while we're talking, mostly to stop myself from talking about peeing, and grossing everyone out, is the concept of statistical significance versus clinical significance. So statistical significance, as we've discussed, is a mathematical concept. And it's a percentage of how confident we are that our results are due to chance alone. That may or may not be relevant in clinical practice. For example, we did a small quality improvement study when I worked at a hospital, an urban safety net hospital, and we found that on average, people of color went 62 days from when they first had a suspicious finding on their mammogram to when they started breast cancer treatment. And white people had an average of 40 days from when they first had a suspicious finding on their mammogram to when they started treatment. They did some math, and the difference was not found to be statistically significant. So in other words, there was a higher than 5% chance that the findings we had were due to, that the difference between groups was due to something other than random chance. It could have been a 6% chance that the findings we had about the difference between groups was only, it was only a 6% chance. We don't really know. We just know it didn't reach that critical threshold of being only 5% or less likely to be due to chance. But even without statistical significance, we need to act on this information. We don't need to wait until we have statistical significance to work on improving time to treatment initiation. that, period of 22 days can be meaningful in terms of outcomes. And the disparity is real, whether or not it's statistically significant. So that's an example of clinical significance. Another example of something that might not be statistically significant, but does have a lot of clinical significance, is something like satisfaction surveys. So if you are, surveying your clients to see how satisfied they are with social work services and how well their needs are being met, and you have several different groups of clients, there might not be a statistical difference, a statistically significant difference in terms of how high different group satisfaction levels are. But if you're getting a lot of answers back that express low satisfaction or that needs aren't being met or people aren't being listened to, that's still clinically significant and still worth acting on. Because we don't need to have, mathematical perfection in order to start doing quality improvement and serving our clients better. It should also be pointed out that in smaller sample sizes, it's harder to get statistical significance. You tend to need a lot of numbers or a lot of people involved to get statistically significant findings. And this can be hard in understudied populations or historically or currently oppressed populations that aren't getting the funding that they need to do research or to find out more about them. So populations who, we don't have enough funding to do a full-on clinical trial with enough participants that it's likely to produce statistical significance. We might have money to do something like a case study, and we might not have statistically significant results. But again, just because the results aren't statistically significant doesn't mean they aren't clinically significant or actionable. I have a midwife story about this as an example I think about a lot. So about 5 or 6 years ago, the guidelines for how often people should get cervical cancer screenings changed. So it used to be that for people in certain age groups who had a history of a few negative screening tests in a row, were recommended that they get a cervical cancer screening test once a year. Then a bunch of research came out and found that there wasn't a statistically significant difference in outcomes between people, and I believe the age was, 30 to 40, I think, was the age range. So there wasn't a statistically significant difference in outcomes among people who had their cervical cancer screening once a year and people who had their cervical cancer screening every 3 years. And so this was one of the, I believe it was the American Congress of Obstetricians and Gynecologists, really picked up on these findings and were and put out new clinical guidelines saying essentially that, for people who are over 30, because there wasn't any statistical significance between people who got screened every year and people who got screened every 3 years, they were now recommending that people get screened once every 3 years instead of every year. And so that, practice guideline went into effect. It was pretty influential. But within that research that was done to look at the, is there a statistically significant difference in outcomes among people who are screened every 3 years versus every year? There were not enough people in the sample who identified as transgender, gender nonconforming. So we didn't have, that study didn't have the amount of people it needed to find statistically significant results about people who are transgender. And another, maybe a year or so earlier, a very preliminary study had come out showing that there was a very small, very, very small increase in reproductive system-related cancers among people who took hormones. And that study also didn't have statistical significance. It was too small. I believe that one was a few case studies. I'm kind of using a community case study design that I can talk to you about if you're interested, but I'm not going to get too into right now. So in this study that looked at the slight increase, that found a very slight increase in reproductive cancers among people who took hormones associated with gender-affirming treatment. Wasn't statistically significant, and there was no statistically significant information about the needs of transgender and gender nonconforming people around cervical cancer screening. So if I was practicing as a reproductive healthcare clinician at that point in my life when that study came out, there wouldn't be any statistically significant information telling me what I should do with transgender and gender nonconforming clients. The recommendation would be have them get cervical cancer screening every 3 years, like with the general population. I wouldn't have done that, though, because there is clinical significance to the study that showed a slightly increased risk of reproductive cancers among people who take hormones. And there was not, and the information about the statistically significant findings about how often people in the general population should get their cervical cancer screening wasn't really inclusive of transgender and gender nonconforming individuals. So for me as a clinician, I would have felt that I would have conversations with my clients who were taking hormones associated with gender-affirming treatment and have a discussion with them, including my recommendation that they continue to get screened for cervical cancer. Obviously, if they had a cervix, if they continue to get screened for cervical cancer once a year as opposed to every 3 years. And so in this recommendation, there isn't statistical significance, but I felt that there's clinical significance. There's clinical reasons that the result might be meaningful or actionable on a clinical level or a practice or program level. And that's where your expertise as clinicians really come in. What does this, regardless of statistical significance, does this research have clinical significance to you? Does it have meaning for you as a clinician, regardless of what the math sides of things say? And again, I think this is another place where funding and larger systems of injustice come into play when we think about what research studies get funded enough to find statistical significance. And what sort of the disparities and differences in how resources for research are allocated might impact which topics and groups and communities' priorities are we able to get statistically significant information about. Okay, so the next thing I want to talk about related to statistics is confidence intervals. And confidence intervals relate to sampling. So as we've talked about before, the idea in random sampling is to come up with a group of people who are participating in the study, who reflect or represent the larger population as a whole. And a confidence interval, here's the technical definition, a confidence interval is a range of values that we are fairly sure our true value lies in. So because we're only collecting data from a sample of people rather than every single entire individual in the United States or even in Massachusetts, that's not very feasible. So instead we're looking for a smaller group of people who represent the United States or the Commonwealth of Massachusetts fairly well. And so confidence intervals provide us a range of real numbers that tell us how confident we can be that our sample is representative of the population that we sampled from. Confidence intervals should always be 95% of higher, 95% or higher, and they're always expressed as a range. So you'll see this in many journal articles. They'll report the finding, and then there'll be parentheses, 95% CI, which stands for confidence interval, and then two numbers with a comma separating them. And so what this is saying is if the study result was somewhere in between 12 and 16, we can be 95% confident that the result that the study found does in fact represent the population. So in other words, if we're saying that we're 95% confident that the real actual value in the entire population, not just within our sample, falls somewhere between 12 and 16. And if it falls somewhere between 12 and 16, we can feel confident that we are that our sample represents the population well. If anyone wants a fun website to look at and learn a little bit more about confidence intervals, I highly recommend this one, www.mathisfun.com. This is their page about confidence intervals. But Math is Fun is the reason I barely passed the math section of the GRE. Also, how I found out that, despite all my hard work on mathisfun.com, when I got such a low score on the GRE math portion and such a high score on the verbal portion, I was in the 99th percentile, and my educational psychologist friend Deborah said to me, "Hey, Nahama, usually when there's, that much of a difference in two different kinds of intelligence, oftentimes that's a sign of having a learning disability. Have you ever thought about getting tested?" So that's really probably the only thing of value to have ever come out of the GRE. So I have another example of a confidence interval. This is not about data. This is an example about a friend of mine who has long hair and wants to have short hair. And as we know, rather than using numbers, we're using pictures here. So at the extreme end of the short hair scale is Sinead O'Connor. At the other extreme of very long hair is someone else who you can't really see their feet because their hair is so long. And the confidence interval is the range, the amount of hair that my friend needs to have in order to feel confident. And it needs to be a few units past Sinead O'Connor, and it has to be some units before the person whose feet we can't see. So this is a range of hair length that my friend will be confident about. If this were a confidence interval in research, rather than having short hair here at the end and very long hair here at the end, we would just have numbers, and we would be looking at, on this line of potential results from, 1 to 100. Within what range, from what to what, can we be 95% confident that the result we're finding is in the same range as the actual true real number in the larger population? So some general rules about confidence intervals. The wider the range of a confidence interval, so if you have something like between 2 and 200, that's a wide range for confidence interval, and it means you probably have a smaller sample size. If the range is narrower, if it's tighter, so from 2 to 6, that's a pretty narrow range, this means you probably have a bigger sample size. Bigger sample sizes have enough people in them that they can make up for, an outlier or two. Whereas in a small sample, an outlier counts for a much higher proportion of the sample, and we get a wider range. because of the, the skewedness of having an outlier there. But a bigger sample can compensate for that outlier. So wide range usually means a small sample size. Narrower range in your confidence interval usually means a bigger sample size. And if you ever see a confidence interval that spans both negative and positive numbers, that's a big red flag. Error bars function a lot like confidence intervals, only they're looking at a way of they're more of an estimate. They're sort of a way of eyeballing the statistical significance and representativeness. So on this error bar here, this first one that's brown, it looks like the actual value was, I'm going to say 18. And the error bar, though, is telling us that were the value that we got as a result, as long as it's in between 16 and 20, we can reasonably assume that it's statistically significant and representative of the population. In general, I think you see error bars a lot less within social science research. It tends to be used more commonly in biology and engineering and chemistry type sciences. I think that's just a convention. There's no real meaning to it. But if you ever do see this, you'll know what it means, that for this value, 10, that for this finding of 10, for us to believe that our finding is representative of the finding in the population as a whole, we can look at the error bars, which shows us that a range of, this looks to me like 7 and 9. So if we get a result that falls in between 7 and 9, we can be 95% confident that our answer, which looks like 8.5 maybe, or 7. No, definitely not 7. I sequenced that wrong. It looks like about 8.5. So the 8.5, our result, fits within that range of 7 to 9, letting us know that we likely have a sample that represents a wider population.